Hey everyone, welcome back to the channel. Today we're tackling a question that might have crossed your mind in science class. Are atoms really mostly empty space? You've probably heard that before, right? That atoms are like tiny solar systems with a nucleus in the middle and electrons whizzing around with tons of nothing in between. But is that really the whole story? Turns out, the answer is a bit more complicated and a lot more fascinating than you might think. So, grab your favorite beverage, settle in, and let's dive into the weird and wonderful world of the atom. We're going to break this down in a way that's super easy to understand, even if you haven't thought about science since high school. Get ready for some mind-blowing analogies and thought experiments. The mostly empty space myth, the classical view. So where does this idea of atoms being mostly empty come from in the first place? Well, let's rewind a bit. Imagine way back in ancient Greece, when philosophers like Democritus were pondering what everything is made of. They came up with this idea of atoms, tiny indivisible particles moving around in empty space. This empty space part was key because it allowed the atoms to move and combine, creating all the different things we see around us. Fast forward a couple thousand years, and we have scientists like John Dalton, who gave us a more modern atomic theory. He pictured atoms as solid little spheres like tiny billiard balls. Again, lots of empty space between the atoms, but not much thought about what's inside them. Then came J.J. Thomson, who discovered the electron. Suddenly, we knew that atoms weren't indivisible after all. He proposed the plum pudding model, where the atom was like a positively charged blob with electrons scattered throughout, like plums in a pudding. It was a step in the right direction, but it still wasn't quite right. The real breakthrough came with Ernest Rutherford's gold foil experiment. He shot tiny particles at a thin sheet of gold, and most of them went right through. But some bounced back, which was totally unexpected. Rutherford concluded that the positive charge of the atom must be concentrated in a tiny, dense nucleus at the center, and that the electrons must be orbiting around it, with mostly empty space in between. This is where the mostly empty space idea really took hold. Think of it like this. If an atom was the size of a football stadium, the nucleus would be a pea in the center, and the electrons would be tiny specks whizzing around in the stands. The rest of the stadium would be, well, mostly empty, right? But hold on a second. This classical picture has some serious problems. According to the laws of physics at the time, these orbiting electrons should be constantly emitting energy, like tiny radio transmitters. And as they lose energy, they should spiral into the nucleus and crash. But atoms don't do that. They're stable. Plus, atoms emit light in specific colors, like a fingerprint. This model can't explain why, so we knew something was missing. We needed a whole new way of thinking about atoms. Enter quantum mechanics. The rules change. This is where things get really interesting and a little bit weird. We need to talk about quantum mechanics. Now, quantum mechanics is a set of rules that govern the behavior of matter at the atomic and subatomic level. And these rules are very different from the rules we experience in our everyday lives. Think of it like this. Classical physics is like knowing how a car works. You understand the engine, the wheels, etc. Quantum mechanics is discovering the car is actually a transformer that can turn into a spaceship. It's a whole new paradigm. One of the key ideas in quantum mechanics is that energy is quantized. This means that energy comes in discrete packets like little bundles. Imagine you're building a Lego tower. You can only add blocks one at a time, not half a block or a quarter of a block. Energy is similar. It only comes in specific amounts. This idea was first introduced by Max Planck, and it was a revolutionary concept. Then Albert Einstein came along and showed that light also behaves like particles called photons. So light, which we always thought of as a wave, can also act like a particle. This brings us to another mind-bending concept, wave-particle duality. It means that everything, not just light, but also matter, like electrons, can behave as both a wave and a particle. It's like saying a basketball can sometimes act like a ripple in a pond. Seems crazy, right? But it's true. This was proposed by Louis de Broglie, and it's been confirmed by countless experiments. So, how does this wave-particle duality affect our understanding of the atom? Well, instead of thinking of electrons as tiny particles orbiting the nucleus in neat little paths, we have to think of them as waves spread out around the nucleus. It's like the electron is smeared out into a cloud of probability. Now, this is where the Schrödinger equation comes in. This equation, developed by Erwin Schrödinger, describes the behavior of these electron waves in the atom. When you solve the Schrödinger equation for an atom, you get a set of solutions called atomic orbitals. Atomic orbitals, no more orbits, just fuzzy clouds. Forget those neat circular orbits you saw in textbooks. Atomic orbitals are three-dimensional shapes that describe the probability of finding an electron in a particular region of space around the nucleus. They're not paths, they're probability distributions. Think of it like this. Imagine you're trying to find a friend in a crowded concert. An orbital is like a map showing you where your friend is most likely to be. They might be near the stage, or near the food trucks, or near the restrooms. The orbital tells you the probability of finding them in each of those areas. These orbitals have different shapes, like spheres, dumbbells, and more complex forms. The s orbitals are spherical, the p orbitals are dumbbell-shaped, and the d orbitals are even more complex. But the important thing to remember is that these orbitals are not empty. They represent the probability of finding an electron in that region of space. The electron is not confined to a specific location within the orbital. It's present throughout the entire region, like a fuzzy cloud. This electron cloud fills the entire volume of the orbital. It's not that the electron zips around in a tiny region within the orbital, leaving most of it empty. The electron is the cloud. The cloud represents the probability of finding the electron if you were to try and pinpoint its location. So the empty space within the atom isn't really empty at all. It's occupied by the electron cloud, which represents the probability of finding the electron. Heisenberg's uncertainty principle: you can't know everything. But there's another important concept we need to understand. Heisenberg's uncertainty principle. This principle, formulated by Werner Heisenberg, states that there is a fundamental limit to the precision with which we can know certain pairs of physical properties of a particle, such as its position and momentum. In other words, the more precisely you know the position of an electron, the less precisely you know its momentum, and vice versa. It's like trying to take a picture of a fast-moving car. If you want to get a clear picture of the car's position, you have to use a fast shutter speed, which blurs the background and makes it hard to tell how fast the car is moving. If you want to get a clear picture of the car's speed, you have to use a slow shutter speed, which blurs the car itself and makes it hard to tell where it is. The uncertainty principle isn't just a limitation of our measurement instruments. It's a fundamental property of the universe. It means that we can never know the exact position and momentum of an electron at the same time. The electron isn't orbiting the nucleus in a well-defined path like a planet. Instead, it exists in a cloud of probability, described by its wave function. This also has implications for the size of the atom. The electron can't be confined to a super tiny space, because then we'd know its position very precisely, and its momentum would be incredibly uncertain. The uncertainty principle dictates a minimum size for the atom, based on the electron's energy. The nucleus, a tiny packed powerhouse. Now, let's zoom in on the nucleus, that tiny dense core of the atom. The nucleus contains protons, positively charged particles, and neutrons, neutral particles. These particles are collectively called nucleons. The nucleus is incredibly small compared to the overall size of the atom. If the atom was the size of a football stadium, the nucleus would be a pea in the center. But despite its small size, the nucleus contains almost all of the atom's mass. It's like a tiny, super-dense ball of matter. The nucleons are held together by the strong nuclear force, which is one of the four fundamental forces of nature. The strong force is much stronger than the electromagnetic force, which would otherwise cause the positively charged protons to repel each other. But the nucleus isn't just a collection of protons and neutrons. Protons and neutrons are themselves made up of smaller particles called quarks, which are held together by the strong force, mediated by particles called gluons. So the nucleus is a complex and dynamic system, filled with particles interacting at incredible speeds. And just like the electron cloud, the nucleus isn't empty either. It's filled with these protons and neutrons, which are in turn filled with quarks and gluons. It's a tightly packed, energetic environment. What about space itself? Quantum fields and vacuum energy, okay? So we've established that the electron cloud fills the empty space around the nucleus, and that the nucleus itself isn't empty either. But what about space itself? Is space truly empty? In classical physics, a vacuum is simply a region of space devoid of matter. But in quantum mechanics, the vacuum is not truly empty. It's a dynamic and fluctuating state filled with virtual particles and quantum fields. Quantum field theory predicts that virtual particles constantly pop into and out of existence in the vacuum. These particles are short-lived and cannot be directly observed, but they have measurable effects on the properties of the vacuum. It's like the universe is constantly testing out different possibilities, creating these fleeting particles that wink in and out of existence. Quantum field theory also describes the fundamental forces of nature in terms of quantum fields. These fields permeate all of space, even in the absence of particles. The vacuum is the lowest energy state of these fields, but it still has inherent fluctuations and energy. One important field is the Higgs field. This field is responsible for giving particles their mass. Without the Higgs field, all particles would be massless and travel at the speed of light. So space is not empty, it is filled with fields. These fields are not simply passive backgrounds, they are active participants in the dynamics of the universe. They mediate interactions between particles, they carry energy and momentum, and they can even create particles out of the vacuum. The very fabric of space is alive with activity. The observer effect. Does looking change everything? Now let's throw another wrench into the works, the observer effect. One of the most perplexing aspects of quantum mechanics is the measurement problem. When we try to measure a quantum system, such as the position of an electron, the act of measurement itself changes the system. Before a measurement is made, the electron exists in a superposition of states, described by its wave function. When we make a measurement, the wave function collapses into a single state, corresponding to the value we measured. It's like the electron is saying, "Okay, you're looking at me now, so I guess I have to pick a spot." This raises questions about the role of the observer in quantum mechanics. Does the observer's consciousness somehow cause the wave function to collapse? This is a topic of ongoing debate among physicists and philosophers. What is considered a measurement that causes collapse? Does it require a conscious observer, or can it be any interaction with the macroscopic world? The implications of the observer effect are profound, and it highlights the interconnectedness of the quantum world. The act of observation fundamentally changes the system being observed, analogies and visualizations, making sense of the abstract. Okay, so all this quantum stuff can be a bit abstract. Let's try some analogies to help make sense of it. Remember the football stadium analogy? Instead of thinking of the electron as a tiny speck orbiting a pea-sized nucleus, imagine a constantly shifting, shimmering cloud filling the entire stadium. The cloud is denser in some areas, but it's present everywhere within the stadium. The nucleus isn't just a static object, it's a seething mass of particles interacting at incredible speeds. It's like a miniature hive of bees buzzing and colliding, and the stadium itself is permeated by invisible energy fields connecting the nucleus and the electron cloud. These fields are like the force fields in science fiction, holding everything together and influencing the behavior of the particles. Another analogy is the ocean. Imagine the atom as an ocean. The nucleus is like a tiny island in the center of the ocean, and the electron cloud is the water that surrounds the island. The water is not empty. It is filled with water molecules which are constantly moving and interacting with each other. The water molecules are like the probability waves of the electron, spread out over the entire ocean. The ocean is also filled with waves and currents, which represent the quantum fields that permeate the atom. These waves and currents are constantly fluctuating, creating virtual particles and influencing the behavior of the water molecules. Or think of it like a hologram. A hologram is a three-dimensional image that is created from interference patterns. The information about the image is distributed throughout the hologram, not localized in any particular point. The atom can be thought of as a hologram, where the information about the electron is distributed throughout the electron cloud. The electron is not a point-like particle, but a pattern of information that is spread out over a region of space. Like a hologram, the atom is more than just the sum of its parts. The interactions between the nucleus, the electrons, and the quantum fields create a complex and interconnected system, redefining empty and the importance of perspective. So after all that, are atoms really mostly empty space? Well, it depends on what you mean by empty. If you mean devoid of matter or energy, then the answer is no. The empty space within the atom is filled with the electron cloud, which represents the probability of finding the electron. It's also filled with quantum fields which permeate all of space. And even the nucleus isn't empty. It's filled with protons and neutrons, which are themselves made up of quarks and gluons. It's more accurate to say that atoms are filled with probability, potentiality, and dynamic activity. They are not simply miniature solar systems with planets orbiting a sun. They are complex and interconnected systems governed by the laws of quantum mechanics. The question of whether atoms are mostly empty space is ultimately a matter of perspective and definition. It highlights the limitations of our classical intuition and the need for a deeper understanding of the quantum world. It's a question that forces us to grapple with the fundamental nature of reality and the limits of human knowledge. It's also important to remember the scale of things. Atoms are incredibly small, and our intuition is based on our experience of the macroscopic world. What seems empty to us at our scale might be teeming with activity at the atomic scale. Think of it like this. If you were shrunk down to the size of an ant, a blade of grass would seem like a giant forest. The world looks very different at different scales. And finally, it's important to remember that our understanding of the quantum world is still evolving. Quantum mechanics is one of the most successful theories in physics, but it is not a complete theory. There are still many open questions and mysteries about the quantum world. Physicists are constantly working to develop a more complete theory that can unify quantum mechanics with general relativity, the theory of gravity. This theory of everything would provide a deeper understanding of the fundamental nature of reality. Conclusion: a universe of interconnectedness. So, to sum it all up, the idea that atoms are mostly empty space is a simplification based on an outdated classical model. In reality, the empty space within the atom is filled with probability, quantum fields, and virtual particles. The atom is a dynamic and interconnected system governed by the laws of quantum mechanics. The question of whether atoms are mostly empty space is ultimately a matter of perspective and definition. It highlights the limitations of our classical intuition and the need for a deeper understanding of the quantum world. The next time someone tells you that atoms are mostly empty space, you can tell them, well, actually, and then you can launch into this whole explanation. But seriously, I hope this video has helped you to understand the atom in a new and more nuanced way. The quantum world is a strange and wonderful place, and it challenges our assumptions about reality. It reminds us that everything in the universe is interconnected, and that even the empty space is filled with potential. It's also a reminder that science is an ongoing process of discovery. We're constantly learning new things about the universe, and our understanding is always evolving. The more we learn, the more we realize how much we don't know. And that's what makes science so exciting. So, what do you think? Did this change your perspective on the atom? Let me know in the comments below. And if you enjoyed this video, please give it a thumbs up and subscribe to the channel for more mind-blowing science explanations. Thanks for watching, and I'll see you in the next video.